Let's take a look at the generalized pigeonhole principle. So this is the same kind of idea as the regular pigeonhole principle, but this one is a stronger result. It actually gives us a better guarantee if you want, okay? So suppose that m, n, and k are all integers, and again, suppose that n is larger than m. So this is the same conditions that we had in the first pigeonhole principle. The only condition that we're adding that's new is that k is an integer that's smaller than n divided by m. Typically speaking, k is taken to be the largest integer that's smaller than n divided by m, okay? Now, what's the generalized pigeonhole principle saying? It says that if n pigeons fly into n pigeonholes, then one pigeonhole will contain k plus 1 or more pigeons. So let's explain that with this example. Suppose that we have 9 pigeons and we have 4 pigeonholes. So again, there are 4 houses, 1, 2, 3, and 4. So in this problem, the n is going to be the number of pigeons, which is 9. The m is going to be the number of houses, which is 4. And let's just for kicks and giggles divide n by m. So if you divide n by 4, it's going to be roughly 2 point something. Okay, so let's say, roughly speaking, 2.2, which the largest integer that's smaller than or equal to this is going to be, let's say, 2. Okay. So what does the pigeonhole principle say? It basically says that when these 9 pigeons come and live in these 4 homes, one of the pigeonholes is going to contain 2 plus 1, which is 3, or more pigeons. Okay, let's test that out. So the first pigeon comes and lands, the second pigeon comes and lands, the third pigeon comes and lands, and these pigeons are very antisocial, so they don't like to be around other pigeons. That's why they're kind of taking separate homes. That's 4 out of the 9. So now another 4 pigeons come and land. So maybe the pigeons kind of bunch up together like this. One goes there, one goes here, the other one goes here, then the other one goes there. So that's so far 8 pigeons. And now the 9th pigeon is gonna come and land. He's gonna live in one of these homes. Well, which home is he gonna live in? It does not matter. Regardless of where that pigeon goes, that last pigeon is gonna go into one of the houses. Maybe it's the 3rd house. Maybe it's in the 1st house. Maybe it's in the 4th house. I have no clue which house he's going to pick, but I'll know that one of the houses will have 3 pigeons or more. Okay, so if the pigeon goes in the 3rd house, then that house has 3 pigeons or more. It has 3. Now, this could happen, or you could have a situation something like this, where the pigeons are very social and they all want to hang out together. Well, in this case, let's say the 9th pigeon comes and hangs out in the 1st house. Does the pigeonhole principle still apply? Is there a house with 3 or more pigeons? Yes, there's actually 2 houses with 3 or more pigeons. So, even though there's some 2 houses at the end that never got used, it does not matter. The pigeonhole principle says one of the pigeonholes will have more 3 or more pigeons. And this happened in actually the 1st and 2nd home in that particular case. Okay, so let's summarize what we just wrote. So if 9 pigeons flew into 4 pigeonholes, then one pigeonhole would contain 2 plus 1, which is 3 or more pigeons. Okay, and so I described 2 scenarios again. In this scenario number 1, the 3rd home is going to have 3 pigeons, which is the house we're looking for. In the scenario 2, the 1st and 2nd home both have 3 or more pigeons. So that's not wrong. That's not a problem. The pigeonhole principle just says that at least one home is going to have at least 3 pigeons. Okay, and again, where did the 3 come from? It's because 2 plus 1, that's what the rule basically says. And 2 is the largest integer that's less than or equal to 9 divided by 4. Okay. By the way, this rule works if k is another integer smaller than 2. It works if the k is 1, or it works if the k is 0. But those are less interesting cases. The 2 is the biggest integer that's smaller than or equal to 9 over 4. That's why we usually like that k. So let's try to give it a shot here with this example, number 6, part 2. Suppose that we have a group of 85 people. Must there be at least 4 with the same last initial? So in this problem, the number of people is basically going to be 85. That's the n. The m in this problem is going to be the last initial, which there are 26 possible last initials. And let's divide n by m. So if I divide n by m, I'm gonna get 85 divided by 26, which is how much? Roughly speaking, it's 3.26, so let's just say 3.2. Again, this is just an estimate. Okay, so what could k be? K could be 0 or 1 or 2 or 3. Okay, I usually like to take the highest possible value, so I'm going to be choosing 3. So what does the pigeonhole principle guarantee? The generalized pigeonhole principle guarantees that k plus 1 will work. So 3 plus 1 is 4, and that's what they are looking for in this case. So yes. So according to the generalized pigeonhole principle, 3 plus 1, which is equal to 4, and I got the 3 from the division of n by m. So 4 people or more actually will have the same last initial.